Chapter 1 Physical Quantities and Measurement. Lecture 0.5 hour, tutorial 1 hour. So this is an overview about this topic. We have three main subtopics, which is the first one is dimension of physical quantities. Second one is scalar and vector quantities, which is consists of vector resolution. And the last part is vector multiplication, which is consists of scalar and vector product. Learning outcome for 1.1, dimensions of physical quantities. Okay, by the end of this chapter, students should be able to define dimension. Okay, second, determine the dimension of derived quantities. And the last part is verify the homogeneity of equation using dimensional analysis. Dimension. Dimension is defined as a technique or method which the physical quantity can be expressed in terms of combination of basic quantities. It can be written as, in square bracket, the physical quantity or its symbol. Table 1.1 shows the dimension of basic quantities. We have 6 basic quantities that you have to remember the symbol of the dimension and the unit for the quantity. Dimension of mass, the symbol is capital M and the unit is kilogram. Dimension of length, the symbol is L and the unit is meter. Dimension of time, the symbol is capital T and the unit is second. Dimension of electric current, the symbol is capital A or capital I and the unit is ampere. Dimension of temperature, the symbol is theta and the unit is Kelvin. And the last one is amount of substance, the symbol is capital N and the unit is mole. The uses of dimensional analysis are: first, to determine the unit of the physical quantity. Second, to determine whether a physical equation is dimensionally correct or not by using the principle of homogeneity. And principle of homogeneity is when the dimension on the left hand side equal to the dimension on the right hand side. And the third part is to derive or construct a physical equation. There are some notes that you have to remember, which is the first one, dimension of dimensionless constant is equal to 1. For the example, dimension of 2 equal to 1, or dimension for refractive index also equal to 1. And the second one, dimension cannot be added or subtracted. Okay, refer to the example 1.1. So you have to determine a dimension and the SI unit for the following quantities. Okay, first refer to the A question, which is the quantity is velocity. First of all, you have to know the definition of velocity. So if you recall your previous lesson, velocity is actually defined as a change in displacement divided by time interval. So to write down the dimension of velocity, remember you have to consider the square bracket, meaning that it is referred to the dimension of velocity, okay, equal to the dimension of change in the displacement divided by dimension for the time interval. So when we coming out the symbol for the dimension, okay, dimension in displacement, meaning that we have referred to the length. So the symbol for length is L. Okay, for the time interval, the symbol for the dimension for time interval is T. Therefore, we also can rewrite the equation as LT negative 1. Therefore, the unit is SI unit. Okay, for length, the unit is meter. And for time, the SI unit for time is second. Therefore, the SI unit for velocity is actually meter per second. Okay, for question B, you have to determine the dimension for acceleration. Okay, so as usual, first you have to know what is the definition for acceleration. and acceleration is actually change of velocity divided by time interval. Okay, and the dimension for acceleration should be, okay, dimension for change of velocity divided by, okay, dimension for time interval. Okay, you may also use the symbol. Okay, so dimension for acceleration, okay, is actually equal to the dimension for velocity, change of velocity, divided by, okay, dimension for time interval, delta t. Okay, so if you still remember, okay, dimension for delta v or delta change of velocity is lt negative 1. And the dimension or the symbol used for time interval, the dimension is capital T. Okay, so the equation is actually lt negative 2. Therefore, the unit is, okay, for the unit, okay, for length, the unit is meter, and for time, the unit is negative 2. Therefore, the SI unit for acceleration is meter per second square. Question E, dimension and SI unit for force. Okay, so first you have to remember what is the formula for force. So we know that force is actually equal to the mass time with the acceleration. Okay, so dimension for force, okay, you may also use the symbol. Okay, so the dimension for force, okay, in square bracket, okay, force equal to the dimension of mass, okay, m, okay, time with the dimension of acceleration in bracket, okay, a. So when we coming out the symbol for mass, okay, remember doesn't need to write down the square bracket anymore. So the dimension for mass is capital M. Okay, and the dimension for acceleration, okay, lt negative 2. Therefore, the dimension for force is actually mlt negative 2. So, the SI unit, okay, for mass, the unit is kilogram. For L, length, the unit is meter. And for the time, the unit is second. So, the SI unit for force is actually kilogram meter per second square. Example 1.2. Determine the unit of K in terms of basic unit by using the equation below. P net equal to Ka in bracket T1 power of 4 minus T0 power of 4, where P net is net power radiated by a hot object, A is surface area, T1 and T0 are temperatures. So how to solve this problem? First, okay, we determine the dimension for the P net. Okay, from the basic formula of power, we know that power is work divided by time. Okay, and work is force time displacement. Okay, and the force is actually mass time acceleration. Therefore, okay, in terms of dimension, so we can rewrite the equation, okay, square bracket of mass time with the square bracket or the dimension of A time with the dimension of displacement divided by, okay, dimension of time. Okay, so when we coming out the symbol for dimension mass, which is M, and dimension for A is lt negative 2, and dimension for displacement is L. Okay, and dimension for time is capital T. So finally, the dimension for P net is equal to ml square T negative 3. Okay, and you should know that, okay, for area, meaning that dimension for area, since area is length time with length, therefore the dimension is L square. And dimension for temperature is actually theta. Next, we rewrite the equation so that the K is as the main subject. Therefore, K is actually equal to the P net divided by A in bracket, okay, T1 power of 4 minus T0 power of 4. Okay, therefore, dimension of K equal to the dimension of P net divided by dimension of area time with the in bracket dimension of, okay, in bracket T1 power of 4 minus T0 power of 4. Okay, and what you should know is, since we know that the dimension cannot be added or subtract, therefore you should know that, okay, dimension for T1 power of 4 is equal to the dimension of T0 power of 4, or we can use the symbol as the dimension of T power of 4. Thus, okay, so the dimension of K equal to dimension of P net divided by dimension of area time with the dimension of T power of 4. Okay, since we already determined the dimension for the P net, which is ML power of 2 T power of negative 3, and then we also had determined the dimension for area, which is equal to L square, and the dimension for the temperature is theta. Okay, so we continue the power of 4. Finally, we got the dimension for K. Okay, after we solve this equation, we got the dimension for K is M T negative 3 theta negative 4. Therefore, the SI unit for K is, okay, for M mass, the unit is kg. For T, okay, which is time, so the unit is second, negative 3. And theta, okay, is for temperature, so the SI unit for temperature is Kelvin. Okay, so the SI unit for K is kg, okay, second negative 3, Kelvin negative 4. Example 1.3. Determine whether the following expressions are dimensionally correct or not. For question A, the equation is 2s equal to 2ut plus at square, where s, u, a, and t represent the displacement, initial velocity, acceleration, and the time of an object respectively. Okay, to solve the problem, okay, we have the equation 2s equal to 2ut plus at square. So to check either the equation is dimensionally correct or not, okay, you have to check the dimension for the left hand side and the dimension on the right hand side. Okay, so first, the dimension on the left hand side, we have the equation is 2s. Okay, so we have to check the dimension for 2s, which is, okay, we separated, okay, dimension of 2 time with the dimension of s, displacement. Okay, so we know that, okay, for dimension 2, any constant value, the dimension is equal to 1. And dimension for displacement is L. Therefore, the dimension on your left hand side is actually L. Okay, for the dimension on the right hand side, the equation is at square. So, we check the dimension for the at square. So, we separated the equation, dimension for acceleration, time with the dimension of t square. Okay, so when we coming out the symbol for dimension of acceleration, which is dimension for acceleration is lt negative 2, and the dimension of time is t power of 2. Therefore, we got the dimension for right hand side is L. So, we compare the dimension on left hand side is L and the dimension on right hand side is also L. Meaning that we can conclude that when the dimension on left hand side equal to the dimension on the right hand side, hence the equation above is homogeneous or dimensionally correct. For question B, we have v square equal to u square minus 2gt, where t, u, v, and g represent the time, initial velocity, final velocity, and the gravitational acceleration respectively. Okay, so as the solution, we have the equation v square equal to u square minus 2gt. So to determine either the equation is dimensionally correct or not, we have to check the dimension on the right hand side and on the left hand side. So for this equation, dimension on the left hand side, which is v square. So the dimension for the v square, velocity square, okay, so the dimension is lt negative 1, okay, square. Finally, the dimension for velocity square is L square t negative 2. For the dimension on the right hand side, okay, we have two equations, two variable, which is u square and the 2gt. So we have to check one by one. Okay, so the dimension for the u square, okay, u is the initial velocity. So the dimension of u square is lt negative 1. Okay, square. Finally, dimension of u square is L square t negative 2. Okay, and for the second quantity, we got the dimension for 2gt. Okay, so you have to determine the dimension for 2gt, which is, okay, dimension of 2 time with the dimension of g, gravitational acceleration, and time with the dimension of time. Okay, for dimension 2, okay, dimensionless constant, so equal to 1. For g, gravitational acceleration or equal to the acceleration, therefore the dimension is lt negative 2. And for time, the dimension is capital T. So that we got the dimension for equation 2gt is lt negative 1. Okay, so thus when we compare the dimension of v square equal to the dimension of u square, but okay, not equal to the dimension of 2gt. Okay, so what is the conclusion? Therefore, the equation above is not homogeneous or dimensionally incorrect.